When we talk about gases, one of the things we got to talk about is how fast they are, which is pretty darn fast. A lot faster. They move a whole lot faster than solid particles and liquid particles do. They move extremely fast. But not every gas in a sample, not every molecule in a sample moves at the same speed. Okay? So I just need you guys to keep this in mind. Not all gases, not all gas particles in a sample move at the exact same speed. Okay? Not all particles move at the same speed. Most of them are moving at the same speed, but not all of them. That is how we end up with what is called a distribution. Yes? If every single gas particle was moving at the same speed, we would just have like a bar graph, right? You would just have one sample, one number of particles all moving at the same speed. But we don't have that. What we have is a distribution. Some of them are moving much slower. Most of them are moving at the average. Some of them are moving much faster. Okay? Distribution. In general, the speed, the average speed, is directly proportional to your temperature. Speed is directly proportional to the temperature. That is because speed is based on something called kinetic energy, which I symbolize KE. In our next chapter, we are going to talk about energy. In chapter 5, we are going to talk about energy, and we'll talk a little bit more about kinetic energy specifically. But basically, what do you guys think kinetic energy is? It's the energy of movement. Okay. Kinetic, movement. Kinesiology, movement. Okay. Kinetic. So we're talking about how the gases are moving, and it is due to how they move, how much energy they have, how fast they're moving is due to what? Directly proportional to what property? Its temperature. Yes. So we can see that a gas at a temperature of 0, which is what this blue line on the graph represents, okay, has an average speed of, I think that says around 1,500 meters per second. Okay, that's fast, all right? If I increase the temperature of this gas, which I think I'm talking about hydrogen gas here, okay, to 500 degrees C, what happens to the average temperature? It increased. Average is now 2,500 meters per second. Is it still a distribution? Yes. Okay. But the average would be calculated by doing what? Truly trying to count every number of molecules and measure each molecule's individual speed, add all of those numbers together and divide by the total. That's how we get an average, right? Okay, that's BS. We don't want to do that. It's ridiculous. This is nonsense to try to do that. So instead, for gases, what we calculate, what we think about is not the average, okay? We are not actually thinking about this average that the majority of the molecules are moving at. We think about something called the root mean square speed, RMS speed. This is what I need you guys to know. If I say how fast is a gas moving, I am not actually talking about the average of a sample. We are talking about this thing called RMS speed, okay? So this formula is on your useful equation sheet, but here it is. This is the symbol. The U right there is the symbol that we use for RMS speed. Okay. RMS speed. RMS speed is equal to the square root of 3 times R, which is the gas law constant. However, I'm fixing to show you guys we're using a different value here. Eek. Okay. 3 times R times T divided by, what does it mean when I write M like that? Molar mass of the gas. Okay, so that's what this is based on. Root mean square speed is based on temperature and molar mass. We already said if it's a hotter temperature, it's moving faster. How does speed relate to molar mass? Think about it. It's an inverse relationship. Yeah, reverse. Inverse relationship. Hang on, we'll come back to that. Look at this. What kind of gases move fastest? Little bitty lightweight gases. The heavier the molar mass, the slower it moves. That's just physics, right? Lighter elements, lighter molecules move faster, heavier stuff moves slower. Okay. So we know that higher temperatures means faster speed. And we know that larger molar mass means slower speed. Okay. That can be just in and of itself a question, just knowing that concept. Which gas would have the higher RMS speed? Okay, if you got a mixture of SO2 gas and oxygen gas. So they're both in the mixture together. That means they're both at the same temperature. I think this is in class number 30, 29, maybe 29. It's just a concept question. Which gas has the faster, higher speed between SO2 and O2? It's got to be O2. Why? It has a smaller molar mass. O2 is 32 grams per mole. SO2 is 64 grams per mole. If they're both at the same temperature, which they are, because they're in a mixture together, O2 is moving faster. Yes, O2 is moving faster. Okay. So if, though, I have you calculate the actual speed number, okay, this is where for this particular problem, this particular formula, you got to know some information. I think all of this is on your useful equation sheet. Okay. All right. You have the formula, yes. In this particular calculation for RMS speed, the R value that we use is different units than what we've been using for the ideal gas law, okay? This is the R value you would use when calculating RMS speed, okay? 8.314 joules. That's what that J is, a joule. This is an energy unit. We're talking about energy, speed, okay? That's why we have a different R value here. You have to use this R value if you're calculating RMS speed. 8.314 joules per mole times Kelvin. Okay. A joule is an energy unit. We will talk more about energy units in our next chapter. Okay. A joule has a definition of these IUPAC units. I'm not worried if you know the definition of a joule right now in this chapter. You need to know to use this R value when calculating RMS speed. Temperature, as always, everything with gas, right? It's got to be Kelvin. Temperature in Kelvin. And then here's the other thing to remember when calculating RMS speed is that your molar mass has to be units of kilograms per mole. Instead of grams per mole, kilograms per mole. That is because of how a joule is defined, okay? To use the molar mass in the RMS formula, you have to have your molar mass in kilograms per mole. That's easy to do. You just divide the molar mass that you add up, divided by 1,000. That takes it from grams to kilograms, right? You have those things, if you remember those things, you write those things down on the note card, you write the formula. All it is plugging in the numbers into this little equation. But you got to know to use these numbers. Look at this example. Calculate the RMS speed of oxygen when it's at 21 degrees C and 15.7 atmospheres. I think this is number 30 on our in class. Here's where I'm being tricky in this problem. To calculate RMS speed, you have the formula that you're going to use. Guys, do you need pressure at all? Does pressure impact how fast the gas is moving? No, it doesn't. What are the only two things that affect how fast the gas moves? Temperature and molar mass. That's it. It's the only two things. So, molar mass of O2, temperature, R. The only thing is now, remember, R is the 8.314 joules per mole Kelvin. And what do I need to do to that molar mass? I can't use it in grams per mole. I have to use it in kilograms per mole. So just divide your molar mass by 1,000. Divide by 1,000. Right? So my temperature, 21 degrees C, is 294 Kelvin, right? My R, 8.314 joules per mole times Kelvin. And my molar mass for O2 is 0.03200. 1, 2, 3, divided 32 by 1,000 kilograms per mole. And all I am doing is plugging those numbers into this formula. 3 times R times T divided by the molar mass, and then take the square root of your answer. And you should get a large number because gases move fast. Okay? It's kind of one of their defining characteristics. I got 479 meters per second because that is the units of speed, of velocity, right? Meters per second are the units for speed. Okay.